All right, so sorry for the false advertising beforehand. This is actually not Gauss Bonnet yet. We're talking about geodesics here for a little bit. So as I say here, the geodesics for a geometric surface are like lines for Euclidean space. So we generalize the notion that they have zero acceleration as we understand it through the perspective of covariant differentiation, right? Again, caution alpha prime prime, that's a mixture of ideas, right? The outside prime is the covariant derivative, the inside prime is the velocity field construction. And so definition, as I told you guys, the curve gamma in a geometric surface is a geodesic, provided that the gamma prime prime is 0. So lemma 1, geodesics have constant speed. Well, that's straightforward from what we did last time, right? We showed that if the covariant derivative was 0, that implies that the vector field has constant length, I think. Here it is, though. So ddt of this is that, and so, yep. So geodesic has constant speed. Lemma 2, if you had an isometry from one surface to another, then the if you have a geodesic in M, then F composed with gamma is a geodesic of N. I threaten that that's one of your homeworks, but I'll leave it at that. But basically, we can push for like the all of the results we had about transporting the connection form and the frame, all of that stuff. What it means for it to be an isometry. There's a connection between the metric on M and the metric on N, and that definition makes this happen. Because again, the definition of geodesic is all baked. It's all based on what? On the omega 1, 2, right? Okay, so how to calculate geodesics? Well, just so you have a sense of what's involved here, let me just talk about it for a couple minutes. Basically, we have the derivative alpha prime for a curve on a geometric surface. Well, we have two functions, v1 and v2, right? v1 e1 plus v2 e2. That gives us the velocity. And then alpha prime prime, you've got a1 and a2, the components of the acceleration with respect to the frame e1 and e2, right? And so the definition of geodesic was that the covariant derivative alpha prime prime, right, of the covariant derivative of the velocity field, namely alpha prime prime, is 0. So since e1 and e2 are independent, that means that both a1 and a2 must be 0 for a geodesic. But on the flip side, we could actually work through the definition of the covariant derivative of a vector field along a curve as given right here, as I wrote on the board today. And when you go through that, that means that a1 is what? It's v1 prime plus v2 omega 2 1 alpha prime, and a2 is v2 prime plus v1 omega 1 2 alpha prime. But those both have to be 0, which gives us a couple of equations. But also, going back to the warping functions, and assuming f equals to 0 here for an orthogonal patch, you get theorem 4.2, namely that a1 has to be given, it is a little a1 prime prime plus this stuff, and little a2 prime prime plus that stuff equal to 0. So if you can solve these differential equations for little a, and the little a1 and a2, what are those? Do you guys remember?
Oh, those
Mm-hmm.
J? No, it's not J.
It's the component functions of the curve pulled back or to the parameter space. It's the preimage of the curve on the surface. It's the
Push it back whenever you find the derivative of it.
Right. It's the curve in the parameter space that when you feed it to the patch, it gives you the curve that you're talking about on the surface. It's x inverse of alpha, if alpha is the curve we're talking about. Yeah. Yeah, and if I'm doing my job on the final, at no point will that come up, okay? Yeah. And as I say, the proof is a calculation, see page 348. But anyway, so I mean, that differential equation, that's a nonlinear differential equation. Like notice, if you think about it, you guys, your differential equations course, you have not solved anything like this. Generally speaking, this e and the g in the denominator, those are functions of u and v. And it's just rather unpleasant what's involved here. However, if let's see here, moving on here. Come on. Let's see here. Do we have a theorem? If you have a vector and a point, well, there exists a unique geodesic at that point for some interval around 0. So at least if you narrow you can find an interval sufficiently small such that, I mean, there's a unique geodesic through that point, all right? But that means that there's a geodesic in every direction, right? Notice that the v is arbitrary here, so lots and lots of geodesics in the surface. Of course, in Rn, you can just use lines, right? Lines give you a geodesic in Rn. Definition, a geometric surface is complete if every maximal geodesic is defined on all of R. So, you know, you can make the domain of a geodesic as small as you like, but if you can make the domain the whole real line, then that's said to be a maximal geodesic. So, maximal geodesic is formed by pasting together geodesics which overlap until as large a curve as possible is formed. So, like if your frame, the frame doesn't, you only have frames locally on the surface, right? So, you make the geodesic going to the edge of one frame, and then you pick up the next frame where it overlaps, and you build the geodesic going from there, and you just kind of like, piggyback, bootstrap perhaps the right word, from frame domain to frame domain to frame domain, and you can build the geodesic going over the whole surface in principle. So like the great circle, it can go on and on. You can make the domain for the geodesic all reals. It doesn't have to. Anyway, this helix is another maximal. Anyway, I really don't have much to say about this, and it's further explained in chapter 8 if you read on. If you take a further course in differential geometry, you'll talk more about this. All right. Let's see here. Lemma 4.5 gives a kind of nicer criteria to find a geodesic, which is, okay, whatever it is. There's a whole other section that I'm skipping that has more on how to find nice equations for geodesics. Yep. Okay, so that brings us to page 32, which is on the Frenet theory of curves and geometric surface. This actually matters. This discussion feeds into the proof of the Gauss Bonnet Theorem, which is like our larger purpose today. So page 32, we'd like to understand. For a curve on a surface, I don't really care about torsion because we're trying to stay on the surface, right? The torsion of a curve in 3 dimensions, it describes how the curve is lifting off the osculating plane, right? And so we don't really care about torsion, but we do care about curvature. And we can still talk about curvature for a curve on a surface, and here's how we do it. Suppose we have a unit speed curve and an oriented surface. We define the tangent to be the derivative, the velocity field of the curve, just like usual. Well, I say as usual exclamation point, but honestly, guys, is it really as usual? I think that as usual parenthetical remark is maybe counterbalanced a little bit by the discussion we had today about how you actually find the velocity field with respect to the patch, right? It's pain. But anyway, in another sense, yes, as usual, it's the derivative, is the tangent. And then the normal you take to be j of t, right? That's that rotation operator, which we can define for any oriented surface. And then the curvature, all right, k sub g. And here the g refers to like g as in metric. Actually, I think g is in geodesic. I'm trying to remember what that little g is for. Oh, it's geodesic curvature. Duh, it's right here. So the case of kappa sub g, it's the function such that the derivative of the tangent is equal to kappa sub g times n. So you could define the geodesic curvature to be t prime inner product with n. N. Well, what's n though? Well, n is j of t here. All right. Okay. When we defined curvature in the Frenet sense, our curvature was necessarily positive. Remember that? The way we defined Frenet curvature earlier in this course, it was necessarily positive. But now the curvature could be positive. This is the geodesic curvature. It can be positive or negative. It's positive if the tangent is turning towards the rotated tangent. It's negative if the tangent is turning away from the rotated tangent. Here's some pictures of that. Let's see if I can kind of trace out what's going on here. So here's our curve, right? And here's the tangent. Here's the rotated tangent. What's happening as the curve goes on? See what happens with this one? The tangent is bending up like that, right? So it's bending towards that j, which is to say that this has positive geodesic curvature. This one here, as you go further along the curve, the tangent is bending down, which is to say it's bending away from that. So that's negative geodesic curvature. So we could either have positive or negative geodesic curvature in this sense. What is really cool is that there's a formula, corollary 4.6 here. If we have a unit speed oriented curve in an oriented region with frame field E1, E2, and phi is the angle from E1 to the velocity field of the curve, all right? It's an angle function, really. Then the geodesic curvature is given, so here's a picture, right? Here's the curve, the velocity field I've done in green, right? And E1 you get from sweeping angle phi from the curve like that. I guess you get the velocity curve from sweeping angle phi from E1 is how we defined it before, right? So I think we sweep from E1 to the field, right? That was our definition. Like the phi angle is 0 for E1. So like we sweep down actually, like that. But in any event, the geodesic curvature is given by the derivative of the inclination angle plus omega 1,2 beta prime. Now, you may or may not know this, but in calculus 3, one of the definitions of curvature you can give is it's the derivative of the inclination angle. So like in calculus 3, this term right here is gone, and like the regular curvature can be characterized as the derivative of the inclination angle with respect to arc length along a curve. That's a possible, sometimes definition of curvature depending on what calculus book you look at. So this is a natural generalization of that. The proof of this is really the stuff we've just been looking at today. So if we set the vector field to be the tangent vector field, the covariant derivative is phi prime plus omega 1 to alpha prime jy. This was that lemma. I think the last thing I wrote on the board was this one, right? That was this guy over here. I think it was this one, this business here. Yeah, I think it's basically lemma 3.4 in the case. It's lemma 3.4 in the case that the vector field y is the velocity vector field. All right. So, let's see here. So the velocity vector field is the unit tangent vector field y, because this is a unit speed curve. So the velocity field is the tangent field. And so that gives us t prime is this. But then what happens when you take the inner product of t prime with j of t? You just get this coefficient right here, phi prime plus omega 1 2 beta prime. That's exactly the theorem. So yes, that's the geodesic curvature. It's just that. Oh, you're fine. You're fine. I know it's a lot. And again, as I was saying at the start of this, if we take the case m is equal to the xy plane, and we use the Cartesian frame, well then omega 1 2 is 0, and the Gaussian curvature is just d phi ds. This is also known as Leibel's formula. And oh, cool. So let's see here. So the acceleration has two pieces. It has the derivative of the tangent field piece directly, right, which is the speed piece. And it's also got this kappa g v squared piece, which we're seeing here. I don't know. For me, there's, this I get. This right here, there's a bit of a jump for me from what we were just doing.
Does it say the dv over dt, that's the speed, right?
Oh, this right here? Yeah, that's the derivative of the speed with respect to time. It's the second derivative of the arc length function with respect to time is what it is, but it's also the tangential component of the acceleration. I'm not sure what this is doing right here, honestly. I wouldn't worry too much about it. All right. Lemma 4.7. A regular curve alpha is a geodesic if and only if alpha has constant speed and the geodesic curvature is 0. So if the speed is constant, that means dv dt is 0. And if the geodesic curvature is 0, that means this is 0. So if those are both 0, then alpha prime prime is 0. So that would be the reverse implication. But the forward implication, if it's a geodesic, well, that means alpha prime prime is 0, which from this formula means that both this is 0 and that. I don't know. Pretty much, once you have this formula, this lemma is immediate, because the coefficients of the t and the n are independent. These are lovely propositions. I wish I had a few more examples of actual geodesics on surfaces. That would improve this discussion greatly. Sorry about that. So finally, a definition Oftentimes in practice, when you're trying to find geodesics on a surface, like the problem of actually finding a geodesic is a pain because they have to be unit speed curves. All right? So well, they have to be constant length. The velocity has to have constant length, right? And that's kind of annoying. And so a useful sort of in-between step is to find what's called a pregeodesic. A pregeodesic is a curve on the surface which has curvature 0, geodesic curvature 0, but maybe it's not unit speed. And you can always take such a thing and then reparametrize it to make it have unit speed. So if you can find pregeodesics, you can make them into geodesics in practice. So, all right, anyway. So, as I said here, I'm going to go now to section 7.6. The rest of 7.5 is useful and nice, but and probably it has a lot to do with making good on the details of what we talked about day 1, namely that the hyperbolic plane with geodesics as axiomatic lines does in fact satisfy. I say it satisfies the parallel postulate. That's the wrong thing to say. The hyperbolic plane does not satisfy the parallel postulate. The hyperbolic plane shows that you can have all the other axioms of Euclidean geometry work, and yet the parallel postulate fails, right? That's the point of the hyperbolic plane, is it has some of Euclid's axioms, but the parallel postulate axiom not follow through. That was the point of the hyperbolic plane. So what I've said here, the way I've said it, not good. All right, just saying. Oh, yowzers. All right, finally to the main event, the Gauss Bonnet Theorem. So, I'll allow it. Let's see here. So this is my old lecture 27. And it begins with a definition. If we have a curve which has, so the domain is A to B, which is a closed interval, right? It's a regular curve segment in an oriented geometric surface. The total geodesic curvature of alpha. All right, so I'm defining this integral. The integral with respect to arc length is the geodesic curvature, which I'm calling the total geodesic curvature of alpha. How do you do it? Well, you take the curvature function, you evaluate at the appropriate point, and multiply by ds dt, integrate over t. I think this is really, I would say that this shouldn't be s of t. To me, what really belongs here is alpha of t. If I'm I mean, it depends on how you want to think about it, but I think the curvature function I would think about as a function of, well, I guess you could think about the curvature function as a function of arc length. I don't know. But anyway, we integrate the geodesic curvature along the curve to get the total geodesic curvature. I do have an example here. A rather unimaginative example. Here we have a circle of radius r, right? Circle of radius r. We're going to calculate the total geodesic curvature of a circle of radius r in the plane. So here it is. So number 1, I take the circle, I parametrize it with respect to arc length. So you can do that by dividing by r in here. And you can check then that this has unit speed. Then here's the tangent, right? Minus sine cosine. And the normal is jt, which is rotation by 90 degrees. And so that gives us minus cosine minus sine. You can kind of see it here, right? Why it's minus cosine sine there. And then so the geodesic curvature we get from the inner product of t prime and this n, which works out to 1 over r, I believe. All right, so in this case, for a circle, the geodesic curvature is 1 over r. There's no subtle issues of like plus or minus or anything here. And so to integrate the geodesic curvature of the circle, I just integrate 1 over r over ds, where ds, of course, goes from 0 to 2 pi r, because we're going around the circle once. And so we get 2 pi r over r, which is just 2 pi. So the total geodesic curvature of a circle, a counterclockwise oriented circle, one time around in the Euclidean plane, 2 pi. If we instead had gone counterclockwise, we gone clockwise instead of counterclockwise, we would have got minus 2 pi. So geodesic curvature is an oriented idea. The direction of the curve matters. All right. Yeah. So lemma. And honestly, this lemma right here is practically the theorem. I mean, it is awful close to the theorem. I think this lemma is about half of the theorem, honestly. And it really rests strongly on what we already did, which was that the geodesic curvature was the rate of change of the inclination angle with respect to arc length plus omega 1, 2 beta prime. All right? And so here's the lemma. You have a regular curve segment, and you want to calculate the total geodesic curvature along the curve segment. Well, it's the difference of the inclination angle function at the endpoints plus the integral over the curve of omega 1, 2. Now this, well, what this really means, this right here, this is the integral of a one form along a curve. So what this actually means is you take omega 1, 2 of alpha prime and you integrate that with respect to time from time A to time B. So here's the details of this lemma proof. Let's look at them. So it's just a straight calculation. So we integrate the curvature with respect to ds. How does that go? So yeah, we integrate from s of a to s of b. So the curvature at time A, the curvature at time b. We take the curvature function as a function of arc length. Arc length is a function of time. And then this, by u substitution, right? We change that to integral over ds. And s of b is sb, and s of a is sa. This is wrong. This should be b, and this should be a. Come on, man. Dude. No. This is supposed to be A. This is supposed to be B, not S of A and S of B. You dummy. Goodness gracious, who wrote this? Sorry about that. And then when we change from integral over dt to integral over ds, then that becomes S of B and S of A, right, by u substitution. As I was telling my students in Calculus 1 this week, change the bounds, for u substitution. But remember, we know that the geodesic curvature is d phi ds plus omega 1, 2 alpha prime, right? And so we have integral d phi ds, which is just the integral of d phi. Again, changing the bounds, that gives me phi of b and phi of a. And let's see here. And over here, I get the integral of omega 1, 2 alpha prime ds, which is, this is actually the definition of that integral. So there it is. This is the lemma. Notice that in the case that the connection omega 1, 2 thing was just 0. It's just the difference in inclination angles, right? Just phi of B minus phi of A. So, yeah. All right. Moving along here. All right. So the arguments which follow here, they're all based on like looking at a rectangle. The image of a rectangle and the patch up to the surface. And the nomenclature that he uses for the edge curves are alpha, beta, gamma, delta. All right. So like alpha bar is the image in the UV plane that maps over to alpha. Beta bar is this is essentially like the A1, A2 that maps to that curve. This is like the A1, A2 that maps to that curve. All right? But this rectangle, R, maps up to x of r over here. All right? And he says, and this is a slight abuse, I mean, I would say that this is the boundary. It's really the boundary of x of r. This is r right here. This is x of r. The boundary of x of r, it's the union, the joining of these curves. It's alpha, then beta. Gamma's going the wrong way, so it's minus gamma. Delta's going the wrong way, so it's minus delta. See, alpha plus beta minus gamma minus delta. The gamma and the delta, they're oriented so that we can use u as a parameter. See this? We can use u as the parameter of alpha bar. V is fixed. U is the parameter of gamma bar. V is fixed. Likewise, V is the parameter of delta bar, V is the parameter of beta bar, U is fixed at two different values here and here. So you've chosen to orient the curve such that we can either use U or V as parameters, and likewise over here. The reason for the minus is because the orientation, if you look at a region, to orient it properly, we have to, as we walk around the positively oriented side, the region should always be on our left, right? So if you can imagine, if this is the upper part of the surface, if you can imagine walking around in the positively oriented sense, the surface should be on your left, and that's what happens if you go alpha, beta, minus gamma, minus delta. Are you guys with me so far? All right, so a lot of jibber jabber just to set things up here.
When you take partial x, why doesn't it like respect partial x u partial x?
Well, that partial x is just notation for boundary.
Okay.
It's an abuse. It's a different use of the word of the partial. And like I said, I really think that would more properly be saying boundary partial xr, to be honest. But anyway, I think I'm following O'Neill. So here's his definition, which I think I just explained. If we have a two-segment, all right, which is a mapping from a rectangle up into a curved rectangle on our surface, then the edge curves of that two-segment are alpha, beta, gamma, delta. And you see how it works? For alpha and gamma, we use u as the parameter. We fix v at c or d, right? Because those are the starting point for v and the ending point for v, right? Starting point, ending point. And the beta delta, we're using v as the parameter, and delta has the initial u, and beta has the final u value. All right? So there are your edge curves. I think you can see why I don't want to write this out at the moment. You know, if I had class 3 times a week, I would write it out and I would go on with my day. But doing 3 lectures, or technically 4 lectures here in a row, there's only so much I can do. All right, so the boundary of x is alpha plus beta minus gamma minus delta, as we said. I say it is a simple closed curve on the boundary of x of r, which is subset of m. I say, oh, flag on the plane, not quite. We have vertices. So it's, I think simple closed curve is true, but the issue is it's not regular. It's not a regular curve because the velocity at the corner points, it's not right. Because those are corner points, so they can't define the velocity at those corner points. Like we have one line segment, we have another curved line segment, another curved line segment, another curved line segment. So each one of those arcs is a
Why don't we just talk about undefined spot?
because the undefined spot is where everything interesting happens here.
Oh.
Yeah, the corners actually matter a lot. But anyway, we can define the total geodesic curvature along the boundary of the two segment to be the sum of the geodesic curvatures along each segment. We just have to take them, we have to add them all together because we can't do them all at once because the edge points matter. We have to break it up into cases, basically. We're forced to do this. Notice, though, that we can, this is an oriented integral. So we can trade minus the curve for minus the integral over the opposite oriented curve. And likewise, we can take the minus delta and change it for minus the integral over delta, like so. All right. Here is an attempt at a picture of what's going on here. So we have x of r, that's what we're integrating over the boundary of. And so we got this integral over alpha, and then beta, and then minus gamma, and then minus delta. What I'm drawing here is you can,
The line segments with relation to the curvature of the surface.
the blue dotted line is, I'm imagining, instead of having the actual corners, like you're taking a dotted line and sort of blowing it out to here, taking the limit as it goes to that, something like that. So let's see here. C is the boundary of x cut corners, but the integral over C is not equal to the integral over the boundary because what happens at the corner actually matters because of the turning. You see the tangent direction just abruptly changes at these corners, right? See how that goes? Like going from alpha to beta. See this? The tangent direction at the end of alpha is like this. And then what's the tangent direction at the start of beta? It's like that. Right? There's this swinging of angle epsilon 2 like that. But what's the geodesic curvature about? It's about the relation of the tangent and how it's, how the tangent direction to the field relates to the normal direction of how the tangent direction is rotating into the normal direction, right? So when your tangential direction abruptly changes, you can't just ignore that and hope to just gloss over it in a limiting process, It's we have to deal with it. Excuse me. But the larger point of this picture is it's defining the so-called exterior angles. All right, so the exterior angle to this point, it's the angle you need to sweep from the tangential direction of the first segment to the tangential direction of the starting of the second segment. And likewise, that was epsilon 2 rather, actually. Epsilon 1 is what you need to sweep from the tangential direction of the final segment, the minus delta 1, into the tangential direction of the start of the alpha 1. And likewise, epsilon 3 and epsilon 4 are defined. Again, it's always the angle needed to sweep from the tangential direction of the previous segment to the tangential direction of the start of the next segment. You can see it in the picture. It's a lot for me to write down, but do you guys know what I'm saying here with the epsilon 1, 2, 3, 4?
Is the swing.
Yeah.
So that's what happened at
Yeah, I mean, if there's an actual corner, then the tangential direction, like, it abruptly changes, right? It's a discontinuity.
Yeah.
That's why you can't define the velocity at those points, technically. I mean, if you tried to define the velocity at those points, which one would you pick, the before or the after?
Well, stop, wouldn't it?
Yeah, or you could just say it stops, yeah.
That's what I would say, because if you have a particle going across that, and it just abruptly changes, it's like a baseball player when he comes around the base, he has to stop going that direction and then
Right.
curve around.
I think that's right. I mean, if he actually,
Or just stop,
if he were,
change direction all of a sudden, you
Yeah.
have to stop and then change direction.
right, and so in a limiting sense, he stops and changes directions. But so definition: let XR be pictured as above. Vertices P1 through P4 as pictured above. The exterior angle epsilon j of x at Pj is the turning angle at Pj derived from the edge curves, alpha, beta, minus gamma, minus delta, in the order of occurrence in x. The interior angle is pi minus Ej. So like the exterior angle and the interior angles are related by these formulas here. Let's look at the, they're not all the same, right? Because it depends on the details. So like, here's the picture for E3. You're going from beta into minus gamma. So your E3 is up here, your theta 3 is over here. So E3 plus theta 3 is pi, right? So epsilon 3 is pi minus theta 3 in that case. The picture zooming in here for 4 is a little bit different. See, for angle 4, you're going from minus gamma to minus delta. And in this case, the epsilon's down here, right? And the interior angle, sweeping from this to that, is actually equal to, theta 4 is equal to E4 here, in this case. Although theta, I've used I in the other page. Uno momento. Oh, no, I'm sorry. I'm a victim of my earlier reading. There's no I here yet. So the thetas are the angles between, I think theta is the angle between XU before and after. The interior angle is pi minus Ej at each one. So interior is always just pi minus Ej. So okay, fine. I think that's consistent. What is this would also be the interior angle here, right? That would be what I would think would be the interior angle from here to here. But that's also pi minus E3, isn't it? Right? How about the next one down? Can we see the interior angle there? See this? So this is the exterior angle, which is congruent to that and so the interior angle here is still pi minus E4.
Okay, hold on.
Wait, oh wait, no.
This is the inside of the shape is over here, right? The interior angle is the angle it takes to sweep from one edge to the other.
Okay.
You guys know, like a square has 4.
Why does E4 equal theta 4?
Because these are alternate interior angles.
I think what my question was.
Sorry, go ahead.
No.
Look, because you're saying theta 4 is in relation to XU, right?
That's
XU
what I'm talking about.
XU is not,
On the
yeah, it's not there. Unless you're, it's not,
Unless you're saying it's from the,
you see what I'm saying? Because if theta 4 was in relation to the line right above where you say P4 is, then E4 would be the alternate interior.
to
Well,
Maybe while we're looking into it too deep.
No, but geometrically, that's
the
you'd have to have a little green line extending past the black line going in the negative direction. Just say that's alternate interior.
the exterior angles, like you said, the sweeping angles from the previous tangential direction sweeping to the new tangential direction, right?
Yes.
The theta, I believe, is the angle from, what is theta here?
But this XU line still is not the
I,
on the axis.
I'm actually not sure what theta is. I mean,
Theta is sweeping from axis to axis, then U4 is also, but that would be saying it's 90 degrees essentially, except in relative to the curve. Like if this was in 2D.
well, here theta 4 is sweeping from from xu to xv.
Yeah, but XU to XV is not the same from negative, well, gamma to negative delta prime.
Negative gamma.
So keep your XU line and take it in the next direction.
Well, but these are like, gamma is like this,
Yeah,
and that is the tangent to gamma is xu.
yes.
Delta is like this, and that is the tangent to delta
Are you
at that
saying
point.
that E4 is going from negative delta, or are you saying it's going to negative delta prime?
E4 is going from minus gamma prime to minus delta prime.
Yeah, then you can't equal theta 4.
Well, but theta 4 is going from minus a minus delta prime to minus a minus delta prime. Like this is minus that,
Yes.
and this is minus that.
How? What?
By definition, essentially, of how we parametrize the edge curves.
So, how do you get two straight lines from that? I mean, I guess they're not line, but how do you get, no, but it have to be two straight lines. Do you see what I'm saying, like geometrically?
I mean, despite my picture's slight crookedness, these are straight lines.
No, not that. I'm saying that the axis of the gamma line, like take out the XU, that line right there, is that not an axis? I'm just gonna come up with
Think about this being an axis and like a direction.
So,
Would you like a laser?
no,
No.
this line here, right?
Mm-hmm.
That line and this line,
Mm-hmm.
that's an angle. But you're saying that this line and this line are the same now, which I don't understand.
Well, this is neither here nor there. It's just these are at this point, like the tangent.
Okay, so you're saying this is a completely different
Like if I had drawn this better, this green line would drop down a little bit. Like you should see that this.
Oh, so
is-
this is not an extension of this line. This green line is the extension of negative gamma prime.
Yes, these are supposed to.
Yeah.
Okay. That was my confusion.
Sorry.
We're saying that
you are
the axis is
victims of my poor artistry.
I'm just like,
Like, I don't say a lot, but they didn't.
I'm just like,
I gotcha.
saying geometry is
I-
false now.
Well, don't think that way. So going back to our my original, more cluttered four-corner picture. So like, this is the exterior angle, right? The interior angle's over here, right? The interior angle here is like down here. The interior angle over here is like there. The interior angle here is like there. And the thetas are, I think theta is the angle between xu and xv
Yes.
at each point.
Well, yes, yeah, essentially, because it is an alternator.
Because we're always switching from a u to a v parameterization at each corner point in this thing. And what's in red here may well define the thetas. I'm sorry, I'm just kind of obsessing over how I've defined theta here. But anyway, I should go on. All right. So theorem, and this is the famed Gauss Bonnet Theorem. Well, part of it. there's actually more to the story that we haven't got to yet, but if we have X is a rectangle, and we have so this is a 2 segment like we were just talking about, and if dm is the area form determined by X, all right, then the integral of the Gaussian curvature over M, so this is a double integral, plus the total geodesic curvature around the boundary of the 2 segment, plus plus the exterior angles, 1, 2, 3, 4, is equal to 2 pi.
Kind of makes sense. Just like you're going around.
Yeah. Let's see here. So star, this is the Gauss Bonnet formula with exterior angles. If you wanted to rewrite this in terms of interior angles, remember that the jth interior angle is pi minus the jth exterior angle. So you can re-express the Gauss Bonnet angle theorem as the sum of the integral of the Gaussian curvature plus the total geodesic curvature around the edge. It's the sum of the interior angles minus 2 pi. For example, for a dumb example, take a rectangle in the plane, right? Take a rectangle in the plane. What's the geodesic curvature of the straight lines that make the edge of the rectangles? Kappa G, 0. They're lines in a plane. They're geodesics. They have 0 Gaussian curvature, 0 geodesic curvature. So that's 0. You're in a plane. I'm talking about Euclidean plane. So the Gaussian curvature is 0. 0, 0. Rectangle. Sum of the interior angles minus 2 pi equal to 0. Is that true?
Yeah.
It is. So there's a quick check on whether or not this is crazy. Let's go through the proof. So it's, I said it's based on using the frame field associated to the 2 segment, namely E1 is 1 over the square root of the warping function times the the u partial velocity, and E2, we're just going to rotate that thing according to this rule that dm of E1, E2 is 1. All right. Now, this business right here, I have not done a very good job this semester explaining it, but it is explained in glorious detail in O'Neill, why that's reasonable. And it's not that surprising if you think about it. You have a 2-dimensional space. You have a defined vector field in one direction. It makes sense that you should be able to define another one by consistently rotating at 90 degrees, provided you have a sense of what it means to, counterclockwise rotate. And it turns out that that is given to you by the existence of a non-vanishing 2 form. That might not be intuitively obvious, as we don't have a lot of experience with 2 forms, but you can flesh it out. Now, that said, remember, definition of Gaussian curvature, d omega 1, 2 is minus k dm, right? But that's also minus k theta 1 wedge theta 2, great. So we have that d omega 1, 2 plus k dm is equal to 0. So that gives us that the integral, the double integral of the 2 form d omega 1, 2 plus the double integral of the 2 form k dm is equal to 0. All right? You guys with me so far? So we're just integrating this 2 form equation over the surface, over the rectangle. Now, Stokes' theorem. Remember I talked to you guys about Stokes' theorem back in the differential form stuff? So the integral of the exterior derivative of a form is the integral of the form over the boundary. All right? Now, technically speaking, that really we're applying it not to we're kind of doing something a little bit sneaky here. We're really applying it to the smoothed out rectangle. That's where the Stokes theorem would directly apply, because Stokes theorem applies to things that have, smooth boundaries. And the rectangle does not have a smooth boundary. It's got a jagged boundary, right? So we have to sort of, actually, what we really need is a slightly modified version of Stokes theorem, which accounts for like piecewise defined boundaries. That's what's really being used here, because that boundary piece has to be understood as all of this, because that's what we just had in that lemma. I don't know if we had that lemma. I guess the lemma is about to come next, but so this integral over the boundary piece from modified Stokes theorem gives us all of this. And once you have all of that, well, that's the theorem, right? So the question is, why is this equal to that? All right. And again, maybe this should be understood in terms of like a limiting process. That's what that picture I had before with the dotted blue line is. You imagine blowing it out, and the limit of blowing that boundary out to the jagged boundary, filling that dotted blue corners into the jagged corners. You go from here to that expression. And that's what hopefully we're going to see on the next page. Oop. All right. So lemma, the integral over the boundary of omega 1, 2 is the integral of the geodesic curvature of the boundary plus the sum of the exterior angles minus 2 pi. So I say that the integral over the boundary of partial x is the integral over these three. And again, I mean, I think, to be honest, like I'm using an extension of the Stokes theorem, really, to piecewise define boundaries. I mean, to be honest, that's what's going on here, I think. Now, each one of these, like...
Oh, and then you pop, yeah, I see where you're at now, actually. Like, because you essentially just take the curvature, the Gaussian curvature,
Uh-huh.
you just pull it out of everything. I don't know where you get the 2 pi from, though. I see where you get everything else.
Well, we'll see here. So the integral of the connection form, remember, we had that lemma. It was the difference of the inclination angles. Plus the integral of the geodesic curvature over the arc lane, over the line segment, curve segment. Blah.
So is that E1? Can you replace that with E1? Rho B minus rho A.
Which what?
Or is that B or rho? It's rho. Yeah, right there.
These are fees.
Oh, phi B minus phi A.
Phi B minus phi A. Yeah.
E1
Let's see here.
of alpha is E1.
Yeah, I don't know.
Phi is the angle function from E1 to alpha theta. Oh, you got 0.
Yeah, I'm not sure why is this 0 here. It's because phi of B is equal to phi of A is equal to 0. This is 0 along alpha, I say. Phi is the angle function from E1 to alpha prime.
Yeah.
But we're working with E1 being partial U, right? So the angle of inclination from XU to XU is 0. All right, so we have to keep track of what we said at the start of this whole thing, you know? That will assumably not be quite the same for the next piece, right? So like this next piece here, omega 1, 2 along beta, remember beta is, beta, it doesn't have U as a parameter, it's got V as a parameter, right? So let's see here. So phi of C so this